Okay, so this video is going to be about water potential. All right, and this little weird symbol right here is water potential. Okay, and water potential is how we determine which way water is going to flow in relationship to all of the particles that are dissolved in a solution. Okay, so a quick little refresher. When you have a solution, it's usually two parts. So you have the liquid part, which is your solvent, and then the particles that are dissolved within the liquid part are called the solute. And together, those two things make your solution. Now, to determine the water potential of a substance or a solution or anything, the formula is the water potential is equal to the solute potential, okay, plus the pressure potential. This looks like a weird little formula. You will always be given this formula, so it's not like you just have to know this out of thin air, but you have to understand how to use it. Potential means you're not actually doing anything, nothing is actually happening, but could it? So with water potential, we're just trying to, if we could calculate water potential, then we can estimate which way water will flow and how fast, or if it won't flow at all. Okay, so with this formula, you have to know what to plug in, all right? And they usually put like a little W here. All right, so the pressure is about a push or a pull on the item that you're talking about. So if we had a container of liquid and we were able to put a stopper down in it and start pushing down, it would create a lot of pressure. If you have some sort of liquid and you have like a syringe and you can suction and pull things up, it would create a different type of pressure. So one of them's going to be a positive pressure and one of them's going to be a negative pressure, and we'll talk a little bit about that more. But in general, most of your pressure that we're going to be dealing with is zero. So when they talk about an open beaker, that means there's no pressure on it. It's just open, nothing's pushing, nothing's pulling. You can always plug in zero for the pressure potential. If they tell you there's a push or a pull, they will then give you the number. They will tell you it's a plus 2.3 or it's a minus 1.5. Okay, they will tell you what the pressure is. You just have to know to plug it in to this spot. You're going to take that pressure and add it to whatever the solute potential is. Okay, so if they tell you nothing, you just plug in zero. So then it's pretty much null and void. But if they tell you there's a push or a pull and they give you the number, you just plug that in and you do algebra. That's just basic math. The solute potential is the one that confuses kids the most. Okay, so solute potential has its own formula, and it's negative I CRT. And all of these things stand for something different. So you need to write these down. You will always be given the formula. You just need to know how the heck to plug things in and what to do. All right, so you should have time. You should have had time to write down that formula. So the solute concentration, that negative is very important. Don't forget that, okay? So negative in front. I is always given as 1 unless otherwise stated. Okay, so your I is the okay, so there was a little technical difficulty there. I'm not sure what happened, but anyway, so I'm going to give you the formula for solute potential, and it's based on negative I CRT. All right, so negative I is your ionization constant. That's what it's called. And it's going to be 1 for sucrose. If it's something different, like I said, they'll give it to you. So for our lab today, since we use sucrose, the ionization constant was 1. But if they told you it was 2, then you would plug in 2. If they told you it was 3.7, that's what you would plug in. This whole formula, you're going to be given all of the parts except for one. And the one part that you won't be given is what you're going to use your lab data graph to actually insert. So on the AP exam, I'll slide this out for a second, you are always given a formula sheet. And the formula sheet always has the water potential formula, okay? So it shows you that water potential is the pressure potential plus the solute potential, and then it tells you what's going on and in a zero, and then it tells you how to calculate the solute potential, and it tells you I, and it says for sucrose, this is 1.0, and then C is going to be your molar concentration. I'm going to show you how to find that. R is your pressure constant. That means it doesn't change. So R is 0.0831, and then all these units that you're not going to worry about right now. And then temperature is Kelvin 273 plus C. So this sheet is always given to you, so you don't have to guess or wonder. You just have to know how to plug in. So I is usually 1 unless otherwise stated. R is a constant. Your favorite word from SAT. R is always 0.0831. Okay, I'm going to leave off the units because I'm not worried about the units right now, but the units are liter times bar over mole of degrees Kelvin. Yeah, lovely. Okay, so your temperature is always going to be in Kelvin. And Kelvin is you take your degrees Celsius and you always just add 273. So normally they'll give you the Celsius temperature. And if I do not give you Celsius temperature, you're going to use 22 degrees Celsius. All right. So that would be your room temperature. Now, if the temperature changed, you would put whatever the temperature was in here and then add it to 273. I'm going to do some examples for you, so don't panic. All right, but then C is the one that is the thing that you use from the graph. All right, and this is your molar concentration of your substance. Okay, so take a second and write that down, and then we're going to go do a calculation of a fake situation. All right, so I'm going to ask you on your lab to give me the water potential of your 3 situations. All right, so you, on your graph, you're going to have your data where you have your line that goes like this. You're going to have a line for the class data. Hopefully it'll be the same. Some of you, yours will be a little crazy. And then you may have like a different line for all 3 classes put together, okay? But this is where we're going to get our data to do our water potential. So we will start off, water potential is equal to solute potential plus pressure potential. All right, in our scenario for our lab, our pressure potential was 0 because we had an open beaker. There was no push or pull, so therefore there's no pressure. So the pressure potential is 0. The solute potential, we're going to have to find by negative I, C, R, and T. Okay, for negative I, we're going to for I, we're going to plug in 1 because we're using sucrose, and sucrose is ionization constant is 1. For R, it's a constant, so we're going to plug in 0.0831. That doesn't change. And then for temperature, we're going to plug in degrees Celsius plus 273. And we did it at room temperature, so we're going to plug in 22 degrees Celsius. So our one piece of the puzzle that we don't know is C. Okay, so we're going to go to our graph. And I'll just use this one that I made up. And this person's molarity, based on their graph, based on where it crossed from positive to negative percent change, it hit 0. So we're estimating it had 0% change, which means that's exactly how much sugar it had in it because it had no change. So we're saying it had 0% change at 0.25 molar solution. Now remember, this is just made up data, so you're going to use your numbers for this, okay? But I'm just going to happen to use 0.25. So for this formula, for the water potential of the potato based on that graph, I would plug in 0.25 because I estimated that it was 0.25 molar the way my graph was graphed. So then I just go down and I do math. I keep my negative. This is 1. This is 0.25. This stays 0.0831. And then I add these two together. And so you're going to have your calculator because you're about to do some other math. So it's 22 plus 273. And that's going to give you 295 degrees Kelvin. Now I'm leaving all my units off because the units get really confusing. And in the end, I'll tell you what units you're supposed to use. So don't even stress about it. All right, so now I'm just going to literally multiply all of this together. So 1 times 0.25 is 0.25. And then 0.0831 times 295 is, 24.5145. Do not round anything yet. And then I'll take those and multiply them together. Oop, I forgot my negative. And so then it's going to be negative 6.128625. All right, and we're just going to round it to 2 decimal places. So the water potential of our potato, or whoever the person's potato was, is going to be negative 6.13. And that's how you calculate the water potential for any substance. So now I'm just going to give you a false number, let you practice it real quick, and then we will try and make sure that you have this down pat. All right, so that one that we just did, I'm going to take that little piece of potato and I'm going to put it in a beaker. And that's the one we just did. And we said that its water potential is negative 6.13. Okay. So now I'm going to make up some numbers, but I want to find the water potential of the solution. So this is the water potential of the potato. Now let me find the water potential of the solution. So I use the same thing. Water potential is equal to solute potential plus pressure potential. The pressure is 0, so that's just going to be plus 0. And so now I need to calculate the solute potential. So I have to use the formula negative I CRT. I have to plug in, this solution is going to be, it'll be we'll make this the 0.8 molar solution, okay? Just making it up. So that means I plug in negative 1 since it's sucrose. C is the molarity, so I do 0.8. R is a constant, and it doesn't change, and it's 0.0831. And then the temperature was the same, so it's 22 degrees Celsius plus 273 Kelvin. So simplifying, I got negative 1.8, 0.0831, and then that's going to become 295. And then I just multiply. So I can just go straight across. I'll leave my negative there. So 0.8 times 0.0831, and then times 295. And I get negative 19.6116. So the water potential of the solution is negative 19.116. And I'll just round it to negative 19.61. Okay? So what happens here is this is the water potential of the solution, and this is the water potential of the potato. This is very important. Water will flow from the lowest potential to the highest potential, in the sense that it goes towards the bigger negative number. Okay? So it goes towards the bigger negative number. So in this situation, the potato is negative 6.13 water potential. The solution is negative 19.61. So that means that the water is going to go out of the potato because it's more negative in the solution. So that makes this solution hypertonic to the potato, and that makes the potato hypotonic to the solution. So the potato loses water to the environment, and the environment gains water. So if you were to put that potato into that solution and you found the beginning mass and the ending mass, you would see that that potato lost mass because it was losing water. And because water is flowing out, this is called osmosis. Osmosis is the movement of water from high water concentration to low water concentration. But when you're doing water potential, it moves from this smaller negative number to the larger negative number.